let's do this one. So the car's position at time t, so position is given by s of t equal to negative 9t squared plus 69t. And there are 4 questions to answer here. The first is, what's the velocity at time t? So what is v of t? Well, the velocity of a object in motion, a car in this case, is just the derivative of position. So the derivative of this, I'm just going to use the power rule, the derivative of negative 9t squared is negative 18t, and the derivative of 69t is 69. That's going to be negative 18t plus 69, and I believe it's in feet per second. So this here is measured in feet. This here is measured in feet per second. So what this is telling me is that at time 0, the velocity is 69. And then at time, in fact, right, let's plug in some. So at time 0, the velocity is 69 feet per second. But then say at time, I don't know, 5 seconds. By plugging 5, negative 18 times 5 is negative 90 plus 69. That's going to be negative 21 feet per second. So what does that mean? Well, it means that the car was maybe the car started, here. It drove this way for a while. It slowed down to a speed of 0, turned around and started driving back that way. So right at 5 seconds, it's going 21 feet per second in the negative direction. So that's what that means when you have a negative velocity. It means you kind of turned around and you're going the opposite way that you were going that was positive. Yeah. Okay. Also, I read you guys' reflections. Some of you got some really thoughtful, nice, cool gifts that were fun to read about. And thank you for telling me about them. I appreciated and enjoyed reading about it. The acceleration of this car at time t, well, the acceleration is just the second derivative of position, or the first derivative of velocity. So that's v prime or s double prime. So we're just taking the derivative of the derivative, and the derivative of the derivative is negative 18. And it's negative 18 feet per second, or feet per second squared. So when you're talking about motion, whenever you take another derivative, you're essentially, it's another per second. So right, position is just measured in feet. The derivative of that velocity is feet per second. The derivative of that acceleration is feet per second, or feet per second squared. And then the third derivative, if you really care, nobody cares, is feet per second, which is also known as jerk, which makes sense, right? Because if you think about accelerating, if you increase your accelerations, right? If you're speeding up and then you hit the gas and you jerk forward and start speeding up even more, that's what jerk is, when your acceleration changes. That would be the third derivative. But again, it's a little weird to think about. So a couple questions to answer now. When does this car stop? Well, when does something stop? When its velocity is 0. So the car stops when the velocity is 0. So we're going to set the velocity equal to 0. It's not going to be a very nice number. So we're going to set negative 18t plus 69 equal to 0. I'm going to add 18t to both sides. So 69 equals 18t, and then t equals 69 divided by 18 seconds, which probably reduces. I think it reduces to 23 over 6. It's not really much nicer, but okay. Yeah. And then finally, when the car stops, what is its position? So this is when it stops at 23 over 6 seconds. So then we're going to plug 23 over 6 into this equation to figure out how far it went, or what is, I should say what its position is, because how far it went is compared to where it started. It does start at 0, so it's the same thing here, but displacement and position are a little bit different. Displacement, yeah. So if I want to find, this is going to be not super fun to calculate. Yeah. S of 23 over 6. I'm just going to plug it in here. And now if I was doing this on a test and it was short on time, I would probably leave it as negative 9 times 23 over 6 squared plus 69 times 23 over 6. In fact, I'm going to leave it like that anyway, because this looks like kind of terrible to simplify. So I would say that's my position. If I was allowed to use a calculator, I would do something else. But right, that's whatever that number is. It's not particularly nice. Yeah. So that's that. Not a terrible question at all. I like that. All right, let's do some. Let's see. Let's do a marginal problem because a couple people asked some marginal questions, and then we'll do some tangent lines. Yeah. Problem is, once we get to like week 7, which is where we're at, we're at the beginning of week 7, different classes kind of start to diverge more. They get further apart. So one class is kind of in one place, the other class is kind of in another place. So trying to kind of address questions from people from both classes. Always good to review. It's also good to see what's coming up, even if you haven't gotten there yet. So let's look at this question, which is use the demand function to find the rate of change in the demand of X for the given price P. So the demand function is X equal to 500 minus P minus 3P divided by P plus 1. And again, so this is the demand function. Just to remind you guys what this means, because I personally struggle with this sometimes. So the demand function, right, it's, gosh, and I was actually looking at the book just to kind of, yeah, so the demand X at the price P. So P is the price, right, which is all, right, all the P's are price. And then the demand, I don't like the word demand. The demand is just the number of units that are demanded at a certain price. So if the price were, I'm assuming this is in dollars, if the price were, let's make something like, I don't know, let's say the price were $10. The demand would be 500 minus 10 minus 3 times 10 might have been not the best choice. Fine, I don't care. 3 times 10 is 30. Over 10 plus 1 is 11. So we got approximately, right, 30 over 11 is a little bit less than 3. So approximately 500 minus 13, which is 487. So, right, there is an example of if you pick a certain price, what the demand is going to be. And then often you can do some sort of solving for price to figure out what price is as a function of the demand. But that's not the question here. The question here is find the rate of change in demand for a given price P, meaning find the derivative. So right, when they say find the rate of change, they're really saying, tell me what the derivative is. So I want to find the rate of change in the demand for the given price P. So we want to know the rate of change in the demand X for a given price P. Meaning we want to find dx dp, how X is changing depending on P. Oh, sorry, there's someone to admit. Did I turn my sound off somehow? I think I turned my sound off. Sorry, if anyone was saying any words, I didn't hear you because I accidentally have my sound turned all the way down. So if you said something and I was ignoring you, I wasn't really ignoring you, I just didn't hear you. If no one said anything, also fine. Just wanted to let you know I wasn't ignoring anybody. So I'm trying to find this derivative here. So take the derivative. I'm going to get, let's see. dx dp. Most of this isn't terrible. Derivative 500 is 0. Derivative negative p is negative 1. Derivative of this, we're going to have to use the quotient rule. So it's going to be minus the bottom times the derivative of the top, which is 3, minus the top, 3p, times the derivative of the bottom, which is 1, all over the denominator squared. So let's see. If we simplify this, we get negative 1 minus 3p plus 3 minus 3p all over p plus 1 squared. The 3p's cancel, and we get negative 1 minus 3 over p plus 1 squared. So it looks like, and this isn't terribly surprising, right? As for a given price, the rate of change in X is -1 minus 3 over p plus 1 squared. So what we're saying here is the rate of change is negative. So I should say, right, when you're talking about the rate of change or something like this, you're asking how is x changing as p increases, right? So dx dp means what's happening to this as this gets bigger, right? We're also talking about the bottom getting bigger. So as the price increases, it doesn't seem unreasonable to say that, oh yeah, the demand for the number of units would decrease if the price is increasing. So x is getting lesser as p is getting bigger. Yeah. Yeah, you could. So, do I want to do that? Sorry, I'm always not great with marginals, to be perfectly frank. We could talk about the marginal here. It feels like not the best example for that, though. So maybe we'll come back to this one after we do another example with a marginal. But if someone said, what's the marginal when x is 10, you would just plug in 10, or sorry, when p is 10, you would just plug in 10 here and you would get some value for x, for how x is changing. I never liked the term marginal, so I will remind you all, when someone says, what's the marginal whatever, the marginal revenue, the marginal profit, they're just asking how much more of that thing do you get if you increase the independent variable, usually the number of units, by 1, right? How much more revenue do we get if we make 1 more unit? Or how much more profit do we get if we make 1 more unit, right? So it's always important to remember that it's if there's only 1 more from where we were, what's the marginal whatever? Let's look at an example. Let's say that we have we have a price that depends on the number of units produced, and the price is 800 minus 0.2x, right? So we, instead of having x depending on price, we're having price depending on x. We could also solve for x here if we wanted to. And then we want to know what's the marginal revenue for producing 100 units. Meaning, if we produce 100 units, how much more revenue do we make for that 101st unit? Okay. And again, marginal is an approximation. So first we have to find the revenue equation, right? Revenue is the price times the number of units, which is going to be, so the price is 800 minus 0.2x times x. So that's going to be 800x minus 0.2x squared. And then to find the marginal revenue for 100 units, we're going to find the derivative, dr dx. Again, really this is just saying how much more revenue do we get as x increases, or what's the change in revenue with respect to the change in the number of units. That's going to be the derivative, which is 800 minus 0.2 times 2 is 0.4x. So then if we plug in 100, so dr dx, when we plug in x equal to 100, this is notation for that, right? Dr dx evaluated at x equal to 100. We're going to get 800 minus 0.4 times 100, which is 800 minus 40, which is going to be 760. So when you're producing 100 units, your marginal revenue, meaning the increase in revenue for producing the next unit, is going to be 760. That seems like it's definitely worth it. And we can actually see that, right? If we actually look at the revenue, so if you look at the revenue evaluated at 100 units versus the revenue at 101 units, if I plug in 100 here, I actually have to do some work here. If I plug in 100 here, let's see, 800 minus 0.2 times 100 is 20. So it's going to be, this is going to be 780, right? 800 minus 20 times 100. versus if we do 101 units. Okay, now the math is going to get a little bit grosser. Let me get out a calculator here. 0.2 times 101. I know I can do that, but let's just be careful here. Is 20.2. 800 minus that. It's going to be 779.8. So this here is going to be 779.8, virtually the same number. Interesting. Times 101. I feel like I'm maybe missing something here. Oh. So if we take the difference between these two, so this is 78,759.8 minus this. You get about 759.8. You get not about, you get exactly 759.8. So the difference here is 759.8. And this marginal here, 760, is a very, very, very good approximation of this actual difference. I think that's, yeah, Marshall, that seems like a valid question. Not that the 16 series is only for that, but yeah, that is certainly one of the reasons. And I feel like it's probably, it might be focused on more so back before your time. There was no 17 series. There was just the 16 and the 21 series. So basically the 21 series was for anyone doing math, physics, chemistry, engineering, probably a couple other specific science majors in there. And then the 16 series was for everything else, including biology. So so there were a lot more biological examples and a lot less kind of econ examples. But now that the 17 series is kind of encompasses all the people doing biology major type stuff, the 16 series does a little bit more focusing on the econ stuff because yes, exactly. 16 series is geared towards like international relations, other stuff, which all have some sort of econ aspect to them. That is my very short, probably not super precise answer to your question, but yeah. Yeah, so really the idea of a marginal is just how much more revenue, how much more of whatever we are calculating do we get if we increase the number of units by 1. In this case, the increase in revenue for increasing one more unit after the 100th unit is approximately $760. It's actually $759.8, but this is a good enough approximation, right? We don't really need to know exactly how much. We just need to know, is it worth it? Yeah, it's definitely worth it here. Whereas if we ask, what's the marginal revenue for producing the 1,001st unit? So if we're making 1,000 units, we want to know how much revenue do we get for making the next one. That's going to be 800 minus 0.4 times 1,000, which is 400. So still a good deal. But then if we say, what is it for 10,000? Well, then it's definitely not worth it, right? Because for 10,000 units, you're going to be losing a lot on the next one. So clearly 10,000 is not the kind of ideal thing. We could also ask the question, because it seems worthwhile, how do we maximize the revenue? Right. Well, to maximize the revenue, you basically want to figure out when the place of the marginal profit is 0. Right. We're increasing the production doesn't increase your revenue at all, but it also doesn't decrease it at all. So you've gotten all of the possible increase out of it, and you haven't gotten into the decrease part. So we would love to know, how do you maximize revenue? And to get the maximum revenue, you're going to take the derivative dr dx, which is, I erased it, but it was 800 minus 0.4x, and set that equal to 0. And then to solve that, right, it's very, very similar to finding when the velocity is 0, because you're trying to find the maximum height of the ball. Same kind of idea here. 800 equal to 0.4x, x equals 800 divided by 0.4, which I would just see as 8,000 divided by 4, right? Move the decimal over 1 on each part, and that's going to be 2,000. So 2,000 units is going to be where we maximize the profit, because 2,000 units is going to be where the marginal revenue is equal to 0, right? Producing the next unit isn't going to give us any more money. Okay. I think that's enough about marginals, I hope. I can always come back to it again. Let me close that one. Okay. Oh, I just did a thing. I didn't mean to. Where'd you go? I pushed a button. No, okay, fine. It's back. All right, cool. Let us. See if I got any other good pens here. You guys both look like you're trash. Sorry. Yeah, all these pens look okay. You've got some. I let my pens sit all like this so I could see how many of them have ink at the bottom, and like there's like 2 of them that do. I've got extra ones. I'm trying to actually not be super wasteful and throw away good pens. So let's look at some tangent line questions. Okay, I got a couple in mind here. I think I might have drank a little too much coffee this morning. I think I'm gonna have to go to the bathroom again, which, yes, I'm an old man who has to pee all the time. Let's see here. So, where'd you go? Oh, you're in here. Yeah. So I want to find the equation of the line tangent. So equation of the line tangent to the following. Y equal to 4x to the 5th minus 5x at x equal to -1. So no big deal, right? This is just point, slope. We have half a point. We can find the slope. So let's find the point first. To find the point, we're just going to plug in -1 for x. And we're going to get y equal to 4 times -1 to the 5th minus 5 times -1. That's 4 times -1, because -1 to an odd power is still negative. That's -4 plus 5, which is equal to +1. So our point is the point -1, comma 1. And then to find the slope, we're going to find the derivative. So the slope, we're going to find the derivative, which is going to be, let's see, the derivative of 4x to the 5th is 20x to the 4th minus derivative of 5x is 5. And then we're going to plug in, again, -1. So y prime of -1 is going to be 20 times -1 to the 4th minus 5. That's 20 minus 5, which is 15. Usually they're going to ask for your equation of your line in the slope-intercept form. I'm going to start in the point-slope form because that's what I usually like. So the equation of the line, I'm going to write it first off as y minus the y-coordinate equal to the slope times x minus the x-coordinate. So y minus 1 equals 15 times x minus -1. And then we're going to simplify it. So this is y minus 1 equal to 15 times x plus 1. We're going to distribute the 15 and get y minus 1 equal to 15x plus 15. And then finally, we're going to add or subtract, depending on what we've got. Right, we're going to get rid of this over here. We're going to add 1 to both sides. We're going to get y equal to 15x plus 16. And that's the equation of our line, our tangent line at this point. Questions about this one? Side of the board here. Okay, let's do one that has some trig. So the trig ones add an extra kind of degree of difficulty because we have to usually be able to evaluate a trig function at a specific value. And I know that's not in everyone's wheelhouse, right? Like a lot of people have forgotten, like, oh yeah, how do I find, cosine of pi over 3 or whatever? So let's look at an example. I'm going to change this one up slightly from what the person who wrote it to me gave me. Let's say we want to find the equation of the line tangent to y equal to 8 cosine of x at the point, let's go 5 pi over 6, comma, well, so the comma should be whatever y is. So I should just actually plug it in and figure out what that is. So let's see. So if I want to find the y coordinate, I'm going to do y equal to 8 times cosine of 5 pi over 6. So for 5 pi over 6, that's actually in quadrant 2. I'm going to use reference angle. The reference angle So just so you guys remember, so right, full circle is 2 pi. Half a circle is 1 pi. 5 pi over 6 is almost a whole pi. Not quite though, right? We're missing a pi over 6/4, right? So if I go to there, right, that's 5 pi over 6. I'm missing a pi over 6/4 to get halfway around the circle. My reference angle, measured to the x-axis always, is how much we need to get, in this case, to a full pi. 5 pi over 6 plus pi over 6 is 6 pi over 6, which is 1 pi. So our reference angle is pi over 6, or 30 degrees if you prefer degrees. So this is a 30, 60, 90 right triangle. And we know for a 30, 60, 90 right triangle, the smallest side is 1, the hypotenuse is 2, and the medium side, which is opposite the medium angle, is going to be the square root of 3. So the cosine of pi over 6, which is adjacent over hypotenuse, is root 3 over 2. I feel like I've made a mistake here. No, maybe not. No, I didn't. So yeah, cosine of pi over 6 is the square root of 3 over 2. But I actually want cosine of 5 pi over 6. Cosine of 5 pi over 6. Well, remembering that all students take calculus, we know that in the second quadrant where this angle is, sine is positive, and the other two, cosine and tangent, are negative. So cosine of 5 pi over 6 is going to be negative square root of 3 over 2. So my y coordinate here is 8 times that. It's 8 times negative square root of 3 over 2, which is going to be negative 4 root 3, right? Because you can cancel a 2 here and a 2 here. So that's my y coordinate, negative 4 square root of 3. Okay. Stop me if you have questions or type them or say something. I do have my volume on so I can actually hear words if you say them. To find the slope, someone's trying to come into class. As soon as I said something like someone's trying to come, I'm like, oh. Let me actually do one thing real quickly here. Everyone's coming in and going. Why can't I see that? One sec, sorry. Just want to try and capture you guys all. There we go. Got it. All right, cool. So find the slope. We'll take the derivative. Just a reminder, the derivative of sine is cosine. The derivative of cosine is negative sine. So the derivative of 8 cosine of x is going to be negative 8 times sine of x. And then if I want to find the slope at this point, I'm going to plug in 5 pi over 6. So y prime at 5 pi over 6 is going to be negative 8 times sine of 5 pi over 6. Which is going to be, so here's the thing, we already know how to find sine because we found cosine. Cosine of pi over 6 was adjacent over hypotenuse, which is root 3 over 2. Sine of pi over 6 is going to be opposite over hypotenuse, which is 1 over 2. And since we're in quadrant 2 for 5 pi over 6, sine is going to be positive. So it's going to be negative 8 times positive 1/2, which ends up equaling negative 4. So we've got a point. We've got a slope. We know how to find the equation of a tangent line. Or I should say just the equation of the line with that point and that slope. So my line equation, written in the point slope form, which is what I like, is going to be y minus the y coordinate equal to the slope times x minus the x coordinate. And then, so this is y plus 4 root 3. I'm going to subtract that from both sides. So I'm going to get y equal to negative 4 times x minus 5 pi over 6 minus 4 root 3. I guess we could distribute to get it in the slope-intercept form. It's not very nice though. So you get y equal to -4 times x is -4x. -4 times -5 pi over 6 is going to be positive 20 pi over 6, which reduces to 10 pi over 3. So plus 10 pi over 3 minus 4 root 3. So there's your slope of 4, and there's your b value, your y-intercept, which is, I mean, it's right. It's 10 pi over 3 minus 4 root 3. There's nothing else to do there. That's what it is. Questions, comments, concerns? Okay. So we're not going to do the next question just yet, but I kind of want to introduce the idea of implicit differentiation by kind of with this next question that we will get back to. I think this was from someone's homework. Yeah. So here's a homework question. Actually, there's two different ones. Which one do I want to use? They're both pretty much the same, actually. Yeah, so we can use either one. We'll probably end up doing both of them at some point. But let's look at this one. So use implicit differentiation to find this one. So this one's actually only asking for the slope. I'm going to write it the way I want to write that. So I want to find the equation of the line tangent to the graph given by the equation xy to the 7th plus 5xy equal to 42. So equation of the line tangent to the graph given by this at the point, what have I got here? At the point 7, 1. Okay, so that's our goal. This thing could be graphed. I'm curious now. Let's actually take a look. We might be able to graph this in Desmos. Sometimes Desmos is, let's see, let me graph it real quick just to see. Xy to the 7th plus 5xy equal to 42. Ooh, okay. Yeah, that does not look very nice. So it's just kind of like x is 0 or y is 0 is the graph. That's interesting and not very helpful. Oh well. So graphing these things occasionally might be nice. Sorry, I got kind of distracted here. No, yeah, Desmos is not the way to go for trying to graph these things that are not functions of one variable. They're not going to give you the graph of the actual thing, which is too bad because it would be nice if it did, but you know, eventually, maybe someday. Anyway, so trying to graph this on Desmos is not going to help you see what things look like. It's fine. So the issue here that you might have realized, we can't solve for y, right? Yeah, we really, right? You got y to the 7th plus a y. You could try factoring out a y. You could, I mean, right? But there's no isolating y in terms of just the other variable x, right? I could say, I mean, this would be wrong. 5xy equal to 42 minus xy to the 7th and divide by 5x. Well, that's a problem, right? Because y isn't the function of y. So the whole idea here is going to be that we're essentially going to pretend that y is a function of x. Because even though it's not strictly a function, right? Like this would totally fail the vertical line test if we tried to actually graph it. So what I'm trying to say here, y still depends on x, right? If we know what x is, y only has a couple possible values. And so when we have something like this, what we're going to do is we're going to implicitly differentiate the whole thing by assuming that y is a function of x and using the chain rule in that way. Let me go to a totally different example. We're definitely going to come back to this, but let's do something else, which is still, I mean, we'll start with the same kind of idea. So let's go ahead and start with, what do I want to do? we'll do that. Okay. Let's say we have the equation something like, yeah, let's do this. I want to try and make it not too terrible. I want to make it that easy. Yeah, let's make it that easy. Y cubed plus x equal to, sure, let's say 8. Yes, I know. We could solve for y here. And we're going to actually. So one way, sometimes, not usually, we can go, is we can actually solve for y. So, and I should say, wait, let me back up one step. I want to find the equation of the line tangent to this thing at the point. Let's say the point, let's go 0, 2. X is 0, y is 2. Yeah, that works. Okay. So one way we could go, which is not going to be our usual route, but let's say we wanted to just solve for y. So y cubed equals 8 minus x. And then y, so to solve for y, we're going to take the cube root of both sides. So y equals the cube root of 8 minus x, which we could totally graph. In fact, I'm going to graph it on the other side, just so you can kind of see what it looks like. So separately here. So y equals the cube root 8 minus x. Not great at graphing this one, but let's see. So here's 8. If x is 8, y is definitely 0. And if x is 0, y is definitely 2. This kind of looks like, yeah, I've drawn better graphs. But that's kind of what it looks like. Sorry. It looks a little not quite as ugly as that. Okay, we'll pretend like this is good enough for now. That's what that graph looks like. It looks like the cube root graph flipped horizontally and then shifted 8 to the right. Okay. So to find the derivative, well, derivative is no problem. We should probably write it as 8 minus x to the 1/3 power. And now we're going to take the derivative and we're going to use the chain rule. So I've got some stuff to the 1/3. My derivative is 1/3 times my stuff to the 1 less power. 1/3 minus 1 is negative 2/3. And then times the derivative of 8 minus x. The derivative of 8 minus x is 0 minus 1. Right? So I've got some stuff to a power. The derivative is the power times your stuff to the 1 less power. And then we have to multiply with the derivative of the stuff. And now let's plug in the point. So I'm going to plug in 0 to, well, just 0. So I'm going to plug in 0 for x. Sorry, I'm just noticing something that I don't love. That's fine. I'm plugging 0 for x. I'm going to get y prime equal to, let's see, 1/3 times 8 minus 0. So 8 to the negative 2/3 times negative 1. 8 to the negative 2/3 is, take it 1/3 times 1/8 to the positive 2/3 times negative 1. 8 to the 2/3 is 4, right? It's the cube root of 8, which is 2, and then 2 squared, which is 4. So I end up with a 1/3 times 1/4 times negative 1, which is a negative 1/12. So one way we could calculate the slope of the tangent line, or sorry, the equation of the tangent line would be to say, okay, I've got my point, 0, 2, I've got my slope. It's going to be y minus 2 equals negative 1/12 times x minus 0. And then we could solve, right, and get y equal to negative 1/12 x plus 2. Which looks reasonable, right? If we look back at the graph here, if I try and draw on the tangent line, grab a, not sure. So I'm out of pens. It's the problem when you throw away all your trash pens, is then you don't have any good trash pens to draw lines on top of lines. Here's a good one, yeah. So trying to draw a tangent line here, right? It definitely has The y-intercept is 0, 2, and it looks like the slope could be negative 1/12. Okay, let's talk about how to do this the other way. And do I have enough room? Yeah, I think I have enough room. Let's go over here. So here's the other idea. And this is kind of super important. So instead of solving for y, because we're not always going to be able to, we're just going to differentiate the whole thing as is, with kind of the idea that y is a function of x. In fact, I'm going to write it that way. Instead of writing this as y cubed plus x, I'm going to write it as a function of x cubed plus x equal to 8. And now we're going to differentiate both sides. What's the derivative of some stuff cubed? Oh, we know how to do that. It's 3 times our stuff squared times the derivative of our stuff. Derivative of x is 1. Derivative of 8 is 0. So it's really, really important to remember that when you're differentiating implicitly like this, the idea is that we are assuming everything is a function of x. So y is a function of x, and x is also a function of x, but it's just x. So the derivative of x is always just 1. So when you differentiate something like y, you end up having to multiply by its derivative. When you differentiate something like x, you also do, but its derivative is just 1. So we kind of don't worry about it. So then we can solve for y prime here. Although we don't even actually have to, but we're going to. Eraser. Trying to make it so I don't yeah, I'm going to erase this first so you can remember that. So if I solve for y prime, look what happens. I have 3 times f of x squared times f prime of x equal to negative 1. And then if I divide by this, don't want to run out of room. I have f prime of x equal to negative 1 over 3 times f of x squared. Okay, so here's the deal. If I was trying to find the equation of the tangent line, I would then just plug in what I know. I know the point is the point 0, 2. So if I plug in 0 for x, there's nowhere to plug in 0 for x. And then if I plug in 2 for y, right? F of x is y. I get negative 1 over 3 times 2 squared, which is negative 1/12, which is exactly what the slope was. More specifically, doing it this way, you actually do get the right answer. So I'm going to write it again. I'm going to leave. Sorry, I know it's a little all over the place here because I'm running out of room. So let me kind of show you the way we would normally do this. Now, it becomes kind of just messy to write f of x and f prime of x. So what we're actually going to do is we're going to say, well, if I take y cubed plus x equal to 8 and I differentiate both sides, the derivative of some stuff cubed is 3 times our stuff squared times the derivative of our stuff. The derivative of x is still 1. The derivative of 8 is still 0. Solving for y prime, we get y prime equal to negative 1 divided by 3y squared. Great. But now look at this. Now you can't always do this, but for problems where you can actually solve for y, I can plug back in what y is equal to. Y is equal to 8 minus x to the 1/3 power. Let me see if I can not run out of room here. I'm going to erase up here. Again, sorry, I know it's kind of gross to write all this up and then erase it. Well, let's plug in what we found y equal to. I'm going to plug that in right here. I'm going to get y prime equal to negative 1 over 3 times 8 minus x to the 1/3 squared. But look, this, those are exactly the same. So if you take the derivative implicitly and then plug back in what y is, or just take the derivative explicitly, you get the same thing. So I make it very, very, very explicitly clear. Doing this implicit differentiation process works. It allows us to find y prime. Now, the problem is sometimes y prime is going to be in terms of x. This example didn't show that. Let me show you another example that's not the one on the other side of the board. I want to leave this one up here because eventually we're going to get to it. So yeah, we'll leave you up here. So here's an equation I think we're all familiar with. X squared plus y squared equal to 25. It's the equation of a circle has a center of 0, 0, a radius of 5. Okay. So I want to find the slope of the tangent line at the point, let's say 3, -4, which definitely is a point on the circle. One way to do this, which we're not going to do, would be to solve for y, take the derivative, plug it in. Instead, I'm going to use implicit differentiation. What's the derivative of x squared? So again, I should back up one step. When you're using implicit, the first step is just to differentiate everything on both sides of your equation. So what's the derivative of x squared? It's 2x. What's the derivative of y squared? Well, again, y is a function of x. The derivative of a function squared is 2 times your function to the first times the derivative of your function. Implicit differentiation is just a fancy word for use the chain rule all the time when you're talking about y. So the derivative of y squared is 2 times y to the first times the derivative of y. I don't usually write the first power there like that. That's just because it's easy to confuse with a prime symbol if you're not careful with your writing. I'm going to erase it, but that's the idea. Derivative of x squared is 2 times x. Derivative of y squared is 2 times y times the derivative of y. You could say, if you wanted to, the derivative of x squared is 2 times x times the derivative of x, but the derivative of x is just 1. The derivative of y is not just 1. The derivative of y is the derivative of y. We could, and I'll do that in a second. Someone asked if we could also solve for y. Yes, we'll do that, and we'll see that it's actually worse, but it's important to see that. And then we have to be careful. The derivative of 25 is 0. So now we're going to solve for y prime, because again, the question was find the slope. So if I solve for y prime, let's see, I'm going to subtract 2x on both sides. So 2y times y prime equals -2x. And then divide both sides by 2y. Y prime equals -2x divided by 2y. I can cancel the 2's. So I get y prime equal to -x over y. And if I plug in the point, y prime evaluated at 3, -4, I end up with -3 over -4, which is going to be positive 3/4. So for this circle, which I guess I'll graph on the other side for just a second. Maybe not for just a second. Maybe I'll leave it up for a minute. So if we look at the circle, center 0, 0, radius of 5. And look at the point 3, -4 right there. It seems reasonable that the slope of the tangent line is certainly positive 3/4. Yeah, that seems reasonable. Seems reasonable. Yeah. Okay. So now let's talk about what if we did solve for y. I can erase all this. Yeah. So I'm going to make a tiny mistake and then we'll fix it to see why it's extra terrible to solve for y. Also, here we couldn't solve for y. So solving for y, usually not an option when you're talking implicit. So but solving for y, so y squared equals 25 minus x squared. And then I take the square root of both sides. So square root of y squared, just y. Square root of 25 minus x squared is just the square root of 25 minus x squared, right? It's not 5 minus x. You can't square root each part individually because there's subtraction there. You just get the square root of 25 minus x squared. Now I left something out there, which we'll fix once we see what the mistake is. Let's go to the other side, just so I can take the derivative. So y is the square root of 25 minus x squared. Sorry, my calf is super tight. Ooh. Yeah. Oh, man. I need to stretch it out. Went for an 8-mile run yesterday, and it's a little just. Okay, sorry. So this is y is 25 minus x squared to the 1/2. Y prime, the derivative is 1/2 times my stuff to the negative 1/2 times the derivative of my stuff, which is negative 2x. Chain rule. Now I'm going to simplify this just a tiny bit. 2's cancel. And I've got a negative x divided by, or I'm going to bring this thing to the negative 1/2 down to the denominator as the positive 1/2. So it's negative x divided by the square root of 25 minus x squared, or 25 minus x squared to the positive 1/2 power. Now check this out. If I plug in x equal to 3, I'm going to get the wrong slope. I'm going to get negative 3 on top, and the square root of 25 minus x squared is the square root of 25 minus 3 squared, which is 9. 25 minus 9 is 16, square root of 16 is 4. It's not plus or minus 4, just 4. So, that's a problem. Here's the problem. When we solve for y, I omitted something. I omitted that it should have been plus or minus the square root of 25 minus x squared. So then, over here, you have a plus or minus, you have a plus or minus, and when you take the derivative, it's really plus or minus negative x over the square root of 25 minus x squared. And then, since we're down on the bottom half of the circle, it's actually the minus part that we're looking at. So it should have been actually minus 3 over 4, which is positive 3/4. That's annoying, right? We don't want to have to think about that. Right? I don't want to decide like, which half of the circle am I using when I can just do it this other nice way. Where you say, oh, y prime is negative x over y, plug in your point, you're done, boom, there's a slope. I will also mention, because it's true, this negative x, so I can rewrite this as negative x over plus or minus the square root of 25 minus x squared, but that's literally negative x over y. So either way, if you can solve for y, whether you do it implicitly or explicitly, you do end up seeing that the explicit way gives you the same derivative as the implicit way. Okay, so I'm going to remind everybody. Now let's kind of go to this example. Unless there's questions about what I did there. So I didn't really have anything more to say. I was just like turning it back to you. So look at it again, see if you had any questions. Let's go to the example that started the whole situation. How do we find the equation of line tangent to this? Well, we're going to start by taking the derivative. All right, we've got the point. We need a slope. So I'm going to find y prime. Take the derivative of both sides. So we're going to have to use some product rules and some chain rules. So the derivative of xy to the 7th. So in fact, let me write out the equation again here. Xy to the 7th plus 5xy equals 42. This is x times y to the 7th. This is 5x times y. So let's use the product rule. Derivative of x times y to the 7th. Derivative of x is 1. Leave y to the 7th alone. Plus, now we flip it. You leave the x alone. And you take the derivative of y to the 7th. The derivative of some stuff to the 7th power is 7 times your stuff to the 6th power times the derivative of your stuff. It's just in this case, the stuff is y. 7 times y to the 6th times the derivative of y. Plus, product rule again. The derivative of 5x is 5 times y. And then flip it, leave the 5x alone, times the derivative of y is the derivative of y. You can also think of it as the derivative of y is 1 times y prime, but I'm just like, oh, the derivative of y is the derivative of y, which is the derivative of y. Let me say it one more time. It's the derivative of y. So if you just got y, its derivative is just y prime. Equal to, derivative of 42 is 0. Okay, so then we're going to, so yeah, we'll do it the long way. So we're going to solve for y prime. So solving for y prime entails keeping all the y primes on one side and bringing all the not y primes to the other side. So I've got, and I'm going to rewrite this just slightly. I'm going to write this as 7 times x times y to the 6 times y prime. And this is going to be 5x times y prime equal to, bring this term and this term to the left. So I'm going to have a negative y to the 7th minus a 5y. Factor out a y prime from the side that has all y primes. So then I've got y prime times 7x y to the 6th plus 5x equal to the same thing on the right, negative y to the 7th minus 5y. Finally, divide by this thing you just factored out y prime from. So that we've got y prime, the derivative, equal to negative y to the 7th minus 5y divided by 7x y to the 6th plus 5x. And now, to find the slope, we're going to plug in x equal to 7 and y equal to 1. So the slope is going to be, so I'm plugging y equal to 1, so I'm going to get negative 1 minus 5 over plugging x equal to 7. So 7 times y equal to 1. 1 to any power is 1. Plus 5 times 7. That's not a very nice number. Let's see, negative 1 minus 5 is negative 6 over 49 plus 35 is 50 plus 34 is 84, right? Negative 6 over 84. 84 is divisible by 6 because it's even and its integers add up to a multiple of 3. 8 plus 4 is 12. So let's see, this reduces to negative 1/14. So then the equation of the tangent line would be, I don't even want to write that part anymore. Let's do it up here. I'm going to be lazy and just leave it in the slope-intercept form, sorry, the point-slope form. It's going to be y minus 1 equal to the slope times x minus 7. Okay, I should point out something important here. Something that's going to make your life easier. If you're trying to find specifically, so if you're using implicit to find the slope of a tangent line, you actually don't have to solve for y prime like this, right? So if they say find the derivative, yes, you have to solve for y prime like this. If they say find the slope of the tangent line, there's an easier way to go. Let me show you. So right here, after we took the derivative of both sides, instead of solving for y prime at that point, plug in the point. And no one says you have to plug in the point at the end. You can plug in the point at the beginning and then solve for y prime. So check this out. Do I have space? That's always the question. Yeah, yes, I can. Man, this feels just awful to me, erasing all the stuff that I want to refer back to. Here's our equation. We don't need the equation anymore. Okay, so there's our slope we found, doing it kind of the hard way. But now check this out. If instead, right after taking the derivative, I plugged in the point, which was x equal to 7 and y equal to 1. Let's see, so I get 1 times 1 plus 7 times 7 times 1 times y prime plus 5 times 1 plus 5 times 7 is 35 y prime equal to 0. To me, it seems a lot easier to solve this. 49 y prime plus 35 y prime is 84 y prime. 1 plus 5 is 6 equals 0. Subtract 6, divide by 84, and you get y prime equals negative 6 divided by 84. Same as over there. To me, this seems a lot easier. So if specifically you're asked to find the slope of a tangent line or the equation of a tangent line, which means finding the slope, you don't actually have to find the derivative implicitly You don't have to solve for y prime. You can plug in your point as soon as you have taken the derivative of both sides, which is nice. I don't think we're going to get to related rates today. Sorry. We'll definitely talk about related rates on Thursday. Let's look at another question. So let's say, so I'm going to give you guys one to start because I thought I could make it to 10:20. Not going to make it. I got to pee. I know. It's like that John Mulaney sketch where he's trying to get, I forget what kind of drug. He's trying to get some prescription drug and he tells the doctor he pees 11 times a day. My friends are like, James, that sounds like you, except not trying to get the drugs. Anyway, sorry, I know it's a little off topic. Why don't you guys try this one? Why don't you find the derivative? So here's our equation. It's very similar to the last one, but not quite the same. It's xy cubed. Yeah, I want to change it. I do. I'm going to change it. So let's say we want to find so x squared y cubed plus xy equal to, let's make it more fun. No, it's not. Let's make it x fourth. Okay. I want you to find y prime, meaning first differentiate both sides. Second, group all the y prime things on one side. So group the y primes. Let's group them on the left and everything else on the right. Finally, factor out the y prime and then divide. Okay. So you're going to have to use the product rule for this piece and for this piece when you take the derivative of the left side. The right side derivative is going to be 4x cubed. Start working on that. I'm going to go pee and then we will see what it looks like. Okay, hopefully you've had some time to work on it and it's not going terribly. Product rule. So this I'm thinking of x squared times y cubed. This is x times y. So the derivative here is the derivative of x squared times the not derivative of y cubed plus x squared, or the not derivative of x squared, times the derivative of y cubed. The derivative of y cubed is 3y squared times y prime, right? Because again, we're thinking of y as a function of x. So you can totally be thinking of this as, oh yeah, it's some function of x cubed. And the derivative of some stuff cubed is 3 times your stuff squared times the derivative of your stuff. It's just the chain. Okay, x, y always seems to throw people off. Product rule again. Derivative of x is 1 times the not derivative of y is y plus the not derivative of x times the derivative of y, which is y prime, equal to the derivative of x to the fourth, which is 4x cubed. Then, so after you do the first step of differentiating both sides, the rest is just a bunch of algebra. We're going to group all the y prime terms together, bring everything else to the other side, factor out, divide. So I'm going to have, and I'm going to write this in what's often called lexicographically, meaning alphabetically. Just a fancy, it's a mathematical way of saying alphabetical, lexicographically. So I'm going to write this as 3x squared y prime plus xy prime equal to 4x cubed minus 2xy cubed minus y. We're subtracting these things to the other side. Factor out the y prime. So I've got y prime times 3x squared y squared plus x equal to the same jazz on the right-hand side here, 4x cubed minus 2xy cubed minus y. And lastly, divide both sides by this to get y prime equal to 4x cubed minus 2xy cubed minus y divided by 3x squared y squared plus x. Most of the time, not always, but a lot of the time, when you're finding y prime using implicit differentiation, it's usually going to be some quotient of things that have x's and y's in it. That is usually the typical result. Questions about this one? Well, I erased the other side. There was one related rates problem that someone asked in discussion. Thank you for asking a question in discussion. I did provide some insight to that question on the discussion. So if you have related rates questions, I know we're not going to get to them today. You're welcome to come by office hours at 3. Also, you can look at the discussion or comment on it, and I will certainly say more things if you have more questions in the discussion post. But definitely Thursday, we will talk about related rates, which also really have a lot to do with implicit differentiation. Let's look at least 2 more examples here. Let's do this one. So use implicit differentiation to find the equation of the tangent to the curve. Okay. So equation to the line of the line, tangent to what have I got here? Xy cubed plus xy equal to 4. At the point 2, 1. Okay, and again, I'm going to point out here, since they're specifically asking us to find an equation of a tangent line, they don't need you to find y prime in terms of x and y. They just need you to find the slope of the tangent line at this one point. So we're going to take the derivative of both sides. Again, a lot of product rules. We're going to get 1 times y cubed plus x times the derivative of y cubed, which is 3 times my stuff squared times the derivative of my stuff. If I was doing the implicit differentiation, I would always think of y as stuff, right? Just like when we do the chain rule, we call the stuff inside another function the stuff, because that's going to remind me that I need to multiply by its derivative. Whereas x is just x. Derivative of x times y, so it's going to be product rule. Derivative of x is 1 times leave y alone plus leave x alone. And the derivative of the stuff is just the derivative of the stuff, which is y prime. Or you could say the derivative of y is 1 times y prime. Still y prime. Equal to the derivative of 4 is 0. Be careful. I've seen a lot of people over the years forget to take the derivative of this and just leave it as 4. It's not 4. The derivative constant is 0. And now, if the question were find y prime, we would do the same algebra we just did before. Right? We would keep this and this on the same side. We bring these 2 things over. We factor out the y prime. We divide by what's left over. We're not going to do any of that. We could totally do all that and then plug in 2 for x and 1 for y and find the slope. But I have found it's usually easier to plug in this now if we're just trying to find the slope. So I'm going to plug in x equal to 2, y equal to 1. I'm going to get 1 times 1 cubed. In fact, you could totally write it out, right? 1 times 1 cubed plus x is 2 times 3 times 1 squared times y prime is what we're solving for. We're not plugging in for it. Plus 1 times 1 plus 2 times y prime equal to 0. So let's see, 2 times 3 times 1 squared is 6 y prime. I should start from the left. Sorry. 1 times 1 is 1. 3, 2, 3, 1 is 6. Y prime. 1 times 1 is 1. 2y prime equals 0. So 2 plus 6 is 8. Y prime plus 2 equals 0. 8y prime equals negative 2. Y prime equals negative 2 over 8, which is negative 1/4. And that's your slope at the point. So then the equation of the tangent line is y minus your y coordinate equal to your slope times x minus your x coordinate. And then you can solve for y if you needed to. I really can't stress enough. If you're using it, so I should actually back up 1 second. If someone says to find the derivative and you see x's and y's all jumbled together on the same side, you should automatically think, oh, I need to use implicit because I've got, right, not solving for y. That's not really going to be a thing here. You could, no, you can't solve for y here. You generally, if you see x's and y's multiplied together, you should be like, I'm not solving for y. I'm using implicit. So when you see them all jumbled up like this, use implicit. And then if it's just find the derivative, you actually have to solve for y prime. If it's find the slope of the line tangent or the equation of the line tangent, we only need to find the derivative at this particular point. So take the derivative of both sides and then plug in that point because it's going to be easier than doing the algebra of solving for y prime. You can totally solve for y prime if you want to. It's just, I wouldn't recommend it if you don't have to. Sometimes you have to. Okay. Like in the words coming out of my mouth, like in this next example that someone asked for. This one, so most of the time these problems are usually just like product rule and power rule kind of chain rule stuff. But this one's slightly different. So the equation is 5x squared y minus 8 over y equals 0. And they want us to find dy dx. Or as I'm going to write, y prime. Y prime is just a little easier to handle when you're writing out this implicit stuff. So to do this one, I would make one adjustment. I don't know. I would simplify this a little bit first just to make it easier. I'm going to write this as 5x squared y minus 8 times y to the negative first equal to 0. I probably didn't leave those parentheses there. Oh well. I'm doing this over water. So then we're going to do the product rule again. Typically, or sorry, we're going to do the implicit again. When I have a constant times a thing with x and a thing with y, I actually kind of like to think of the constant as being attached to the x part. So I can think of this as 5x squared times y. It's just easier. I mean, you could say it's 5 times x squared y and then leave the 5 out and do the product rule, but I think it's easier to do it that way. So differentiate both sides. Derivative 5x squared, so product rule here. Derivative 5x squared is 10x times y. And then leave the 5x squared alone. Derivative of y is y prime. Excuse me. Minus 8 times, right? So constant multiples hang out. Constants on their own have a derivative that is equal to 0. So derivative of negative 8y to the negative first is negative 8 times the derivative of y to the negative first. Okay. The derivative of some stuff to the negative first power is negative 1 times that stuff to the negative 1 minus 1, which is negative 2, times the derivative of that stuff equals the derivative of 0, which is 0. This is one of the reasons I think people sometimes forget that the derivative constant is 0 because they're like, oh, well, 0 is 0, so 42 should be 42. No, the derivative of 42 is 0. The derivative of 0 is also 0. Anything I want to say about this before I start doing stuff? I feel like there is, but I'm not quite sure. No, I guess not. Okay, so then we're going to solve for y prime. So this always involves, for me, making sure I've identified the terms that have y prime. That has a y prime. That has a y prime. That does not, so that's going to the other side. I'm going to subtract 10xy from both sides. Oh, I know what I was going to say. If you're doing implicit, it should always be an equation. You should always have something equal to something. So there's always two sides to deal with. Even if the right side is 0, you still have to keep that 0. That's what I was trying to say. You need this to be equal to 0 so you can solve for y prime. On the left, I'm going to have, let's simplify this just a tiny bit. 5x squared y prime minus 8 times minus 1 is positive 8. So I've got positive 8 y to the negative second times y prime. Let's factor out a y prime. Y prime times 5x squared plus 8y to the negative second equals a negative 10xy. And then divide both sides by this. So y prime equals negative 10xy divided by 5 squared plus 8y to the negative second. Now let me talk about this answer for just 1 sec. I know it's time. If you got to go, you got to go. No problem. But I want to talk about this for 1 second because most people probably wouldn't leave their answer like this. And here's why. This really looks like negative 10xy divided by 5x squared plus 8y to the negative second is 8 divided by y squared. And we don't really like having fractions in fractions. It doesn't look very easy to read. Let me try reading that again. So what we often do with this is we then multiply the top and bottom by that denominator. So that we end up getting, let's see, negative 10xy times y squared is negative 10xy cubed. And in the denominator, we have 5x squared times y squared plus 8. Like 8 over y squared times y squared is just 8. This is probably how you're actually going to see this answer. Yeah, there's totally another way you could do this question, which is kind of funky. Again, you're all welcome to go if you want, but let me just show you one other thing because sometimes people do crazy stuff with this. Another way you could tackle this problem, which is I really wanted to do it on the same board so you can see how totally different the answer looks, is technically it's totally viable to multiply both sides by really kind of anything you want. You can multiply by y. So this is going to be 5x squared y squared minus 8 equals 0. And then differentiate both sides of this. You get a totally different looking answer. Right? If you differentiate both sides of this, you're going to get 10x y squared plus 5x squared times 2y minus 0 equals 0. And if you solve for y prime, you're just isolating this. So you've got 10x squared y prime. Bring this over to the other side equals negative 10x y squared. And if you solve for y prime, sorry, this looks dumb. Y prime is negative 10x y squared divided by 10x squared y. Yeah. And so cancel 10, cancel an x, sorry, an x, stop an x down here, cancel a y. You end up with negative y over x, which does not look at all like this. But if you solve this for y and plug that in here, they actually do end up looking the same, which is just kind of bonkers. Don't worry too much about this, though. I don't think this is what's intended, but you never know. Sometimes people teach kind of weird things. So generally, here's what I would say about implicit. Don't mess with the original equation, right? Like, even though you might be like, oh yeah, let's multiply both sides by y, it's usually probably not a good idea. So I would work with this and do what we did originally, not what I did over here.